Question 11A is worth 1 mark, and you've been given two graphs and a bounded region between the graphs, and the graphs are y equals -1 plus sec x on 5 and y equals 0.1 x squared, and they've been given over a certain domain. You can glean from the diagram that the graphs intersect at the origin and at a point A. And in part A, which is worth 1 mark, we are asked to find the coordinates of A. Now, this is a 3-part question, so although it's going to take us a little bit of time to answer part A, we will save some time because what I'm about to do is assign f of x and g of x to be those functions, and then we'll be able to answer parts B and C more readily. So first of all, open up a calculator application, and we're going to assign f of x to be -1 plus sec x on 5. So let's begin this process. So f, open bracket, x, navigation pad to the right, control symbols template to access the assign symbol, then -1 plus, you can either type in sec or you can press trig and go across to highlight sec, enter, and then x divided by 5. You could also use the fraction template there and press enter. And we will also assign g of x, g, open bracket, x, navigation pad to the right, control symbols template. We'll assign g of x to be 0.1 multiplied by x squared, and press enter. So we have our two functions there assigned, and what we'll do now is we'll exploit that and get a picture up on a graphs application showing these two graphs. So I've already added a graphs application. So the way to add pages, just as a reminder, if you press Control Doc, and then you can add a page as you see fit. So add a graphs page. I'll go back to 1.2. Okay, so what we can do now is f of x and g of x have been assigned. So if I type in for f1 of x, f, open bracket, x, and then press enter, we get our sec function. And then if I press tab, brings up the entry line again. And this time we'll type in g, open bracket, x, and press enter. Now, the picture at the moment doesn't really look like the diagram in the question. And what we need to do is we need to think about changing the window so that it looks a lot like the diagram in the question. So to do that, we'll press menu, and then we will select window zoom by pressing 4, and then 1 or enter for window settings. And what we can do here is we can say, well, okay, let's have an x min, say -0.5. Press tab. We're not quite sure where the x coordinate lies just at the moment, so let's stick with 10 just for now for x max, and we can always adjust. We have an x scale, make that 1. Press tab. We can have y min of -0.5. Press tab. And y max, again, we're not quite sure. We'll leave it as 6.66, etc. just for now. And if need be, we may need to make an adjustment. And we can change the y scale to 1 and press enter. Okay, what we can see there is we can see that point of intersection, which is denoted by point A. We could make a couple of quick edits there. We can double click on that endpoint there of 10 and say change it to 8. Press enter. And that looks quite good. What we can glean is that the quadratic is the top curve and the transform sec function is the bottom curve. And what we need to do is we need to find the coordinates where they intersect. Okay, so there are two ways we can do that. When there's multiple intersection points, I like to go into geometry points and lines and intersection points rather than going into analyze graph and then setting up a lower bound and an upper bound and obtaining an intersection point one at a time. So what we'll do is we'll head towards geometry. So we'll press menu and then we will select geometry by pressing number 8. Then we will one or enter for points and lines. And then we're going to select intersection point or points by pressing number 4. Okay. And you can see up the top left-hand corner, we have that intersection points icon, and it gives you some information. It says, click on the first graph and then click on the second graph. And when we say click on the handheld, that means use the center of the navigation pad. So I'll make contact with the first graph, click on that. Then I'm going to make contact with the second graph and click on that. And I've clicked again to anchor those coordinates to the screen. Press escape to get out of intersection points. And what we see there is the coordinates for point A. And notice here that I'm in float 4. So to change settings, what you would do is press menu, then 9 for settings. And you can see there my display digits is float 4. Press escape. And the coordinates of A, we're asked to express them correct to 2 decimal places. So correct to 2 decimal places, the coordinates of A are 7.00 and, or the Y coordinate, 4.90. Now, there is an alternative way to answer this question, and I'll show you this now by going back to a calculator application. So back to where we assigned the two functions. What we can do is we can use the numerical solve with a condition to find where those, or find the x coordinate of where those two graphs meet. So let's do that. So if we press menu, and then it's, let's select algebra by pressing 3, and then 1 or enter for numerical solve. So our nsolve command now appears on the screen. And what we'll say is we'll say, well, okay, we want to solve f of x equals g of x. Notice that f and g are bold and non-italicized, which is good. We want to solve for x, which is the independent variable, so comma x, navigation pad to the right. Now what we need to do is we need to say, well, okay, for x greater than 0, they only meet at 1 point, so let's add that constraint. So to do that, we will press Control equals, and then navigation pad to the left to highlight the with or the given symbol. It's the same symbol that's in conditional probability. Press enter. And now we simply add the condition x, and we want greater than 0. And we press enter. And so we obtain that x coordinate there, 7.00303. And what we can now do is we can say, well, all right, let's substitute that either into F or G. So if we type in F, open bracket, go up and grab that output, press enter, enter, that gives us the corresponding y coordinate. So that's an alternative way of answering part A. So it's a 1 mark question. Coordinates of A, correct 2 decimal places, are 7.00, 4.90. Question 11b is worth 1 mark, and we're asked to calculate the area of the shaded region that's bounded between the two graphs. What we're going to do first of all is show you a graphical approach, and then we'll show you an approach using the calculator application. The one I would privilege here, and the one that takes the least amount of time, is the graphical approach. So the two graphs you can see there on the screen, point of intersection, all looks quite good. So what we're going to do is we're going to press menu. We're going to select Analyze Graph by pressing number 6. And then the command we want is Bounded Area. And we'll access that by pressing number 7, Bounded Area. Now we get a warning here, which we can ignore. So we press OK. And what we've got is we've got a dashed vertical line and a prompt asking us for the lower bound. Now, what we need to do is we need to say to ourselves, okay, this bounded area, the first intersection point is at the origin and the other intersection point is at point A. So what we can do is we can actually enter the number 0 for the lower bound. So 0, notice that you can see it comes up in a little box on the screen, and then press enter. Now we have a prompt for the upper bound, and the approach here would be to move your cursor. So use the navigation pad, move the cursor until you make contact with that intersection point there, which I've made contact because it's telling me that I've made contact, and then press click or enter. And we can see now that that bounded region is now shaded. And we can also see at the bottom of the screen, a number has appeared, and that number there is, put it inside there, that is a measure of the area of the shaded region. So we've been able to find that quite readily. The area of the shaded region, corrected 2 decimal places, is 6.14. Okay. An alternative approach, which I'll just show for completeness, is to use the calculator application. So control navigation pad back to page 1.1 where we had our functions assigned. Now what we can do is we can assign the x coordinate of that point of intersection. Let's call it A. And we will assign it, so control symbols template, we'll assign it to be the solution to this equation. Press enter. Now, the power of doing that is that we have basically stored 7.00303 as A. And now let's perform a definite integral calculation on the calculator application. So what we can do now is we can use this neat shortcut. We press Shift plus, the definite integral template is now pasted onto the screen. Now let's first of all enter the lower limit, which is 0. And then navigation pad up. Our upper limit, we can have that as A. notice there that it's bold and non-italicized. So A is going to be that 7.00303 number. Navigation pad to the right. Now it's going to be the top curve minus the bottom curve. The top curve is g of x, so g open bracket x, navigation pad to the right, minus f open bracket x. In navigation pad, we want to fill that in with respect to x, so dx, and press enter. And so we get an answer there of 6.14338, which when we round correct to 2 decimal places, the area of the shaded region is 6.14 square units. Question 11C is worth 2 marks. And what we're asked to do here is we're asked to consider that the shaded region has been rotated about the x-axis, been rotated 360 degrees or 2 pi radians around the x-axis to form a solid of revolution. And we're asked to determine the volume of this solid. Okay, so what we need to do is we need to form the definite integral that represents the volume of this solid. Okay, so first of all, what we're going to do is we're going to press the pi button, and pi is highlighted there, so we'll press enter. Then the multiplication key. Now we press shift plus, and that gives us the integral template. Our lower limit is 0, and our upper limit is a, which is that 7.00303, etc. Now we go down with the navigation pad. Now it's time to formalize our expression. And what it's going to be is it's going to be g of x all squared minus f of x all squared. In other words, 0.1 x squared all squared minus, then in brackets, -1 plus sec x on 5 all squared with respect to dx. So we just need to enter this carefully, and it's easier to enter with those functions assigned as f of x and g of x respectively. So let's first of all, let's type in g open bracket x, then navigation pad to the right and press the x squared button, then subtract f open bracket x, then navigation pad to the right and press the x squared button. So that looks to be quite okay. Navigation pad to the right again, and let's enter x there and press enter. And we get a volume of 69.7584, etc., etc. Now, what we need to do is we need to round this to 2 decimal places. So the approach we can use here is we can press menu, then we're going to select number by pressing 2. Then we're going to select number tools by pressing 8, and then round 1 or enter. Go up and grab the last output, then separate that and the number of decimal places that you want to round to by a comma, 2, press enter, and correct to 2 decimal places. The volume of this solid is 69.76 cubic units. Question 12A is worth 2 marks. We're given a complex number z, which is equal to -3 plus 2i. And we're asked to use the binomial theorem to find z cubed. Now, as this question's worth 2 marks, you will need to show use of the binomial theorem. So you will need to write -3 all cubed plus 3 times -3 all squared multiplied by 2i plus 3 times -3 multiplied by 2i all squared plus 2i all cubed. But what we can do, and then simplify that to obtain 9 plus 46i. But what we can do on the Nspire is that we can confirm our use of the binomial theorem. And because this question consists of 4 parts, what I think is a prudent idea is to assign z. So we'll press z, control symbols template. We'll assign z to be -3 plus 2i. And to find the I, press pi, navigation pad, scroll across 1 to highlight complex number I, press enter, enter. Okay, so we've got z there has been assigned. Now, here we'll confirm our by hand mathematics. We will enter z cubed, so press z, then the exponentiate key gives you a superscript, enter 3, press enter, and we obtain 9 plus 46i. So really, using Nspire in part A is as a confirmation of your by hand mathematics. And so hopefully those two match. Question 12b is worth 1 mark. And here we are asked to convert z into the form r cis theta, where theta belongs between -pi and pi, not including -pi. So what we are going to do is we're going to take our complex number z and we will convert it into polar form. It can be done via the catalogue, but we can also do it via menu. So what we will do is we will press menu. We will select number by pressing 2. We will select complex number tools by pressing 9. And we will select convert to polar by pressing 6. And that's saying, let's take our complex number and express it in polar form. And we press enter, and notice that we get an exact answer. What we can do is, if you have a look at your, above the enter key, there's an approximately equal sign. Press control enter, and it gives us the decimal form for complex number z. And the way to interpret this is that z is equal to, and this is correct to 2 decimal places, 3.61 cis 2.55. Okay, remember that the Nspire doesn't give complex numbers in cis form. Nspire gives complex numbers in Euler or exponential form. Okay, so the answer to question 12b is that z is 3.61 cis 2.55, correct to 2 decimal places. And you can tell that 2.55 is within that bound of -pi to pi for theta. And also ensure in this question that your mode is set to radians. Question 12c is worth 2 marks, and we're asked to use part B, or the result from part B, to determine z cubed using de Moivre's theorem. And we need to express the answer form in the form r cis theta, where theta belongs between negative pi and pi, and not including negative pi. Okay, so basically z cubed is equal to, and including an extra decimal place, z cubed is 3.605 cubed cis 3 times 2.553, which is equal to 46.872 cis 1.377. Now what we can do is then we can say, well, all right, let's express this correct to 2 decimal places. So z cubed is 46.87 cis 1.38, correct to 2 decimal places, where that argument or angle 1.38 lies between negative pi and pi. What we can do here is we can use the Nspire. So I think what I would do here is I would write down z cubed equals 3.605 all cubed cis 3 times 2.553, and then I would go to the Nspire and get it to calculate for you z cubed and convert to polar form. So what we'll do is we'll press Z, the exponentiate key, z cubed, and then nav pad to the right, just to make sure that the cursor's down level with Z. Let's press menu. Let's select number by pressing 2. Select complex number tools by pressing 9. And select convert to polar by pressing 6. And press enter. Once again, we get an exact answer, but if we press Control, enter, there we get our decimal answer. And what's really good is that it's already in the required form, particularly involving the required value for theta. And so to express this in terms of cis form, z cubed is 46.87 cis 1.38, correct to 2 decimal places. In 12D, we're asked to evaluate the reasonableness of our results from Part A and Part C. And there's a note there that the two methods should give the same results. Okay, so this is a 2-mark question. Currently, we've got z cubed expressed there in polar form, and what we first of all should do is convert that form of z cubed into Cartesian form and compare it to the Cartesian form for z cubed that we found in Part A. So I could go up, highlight it, press enter, and then what we might do is we'll edit this correct to 2 decimal places. So we're just knocking off some digits there. And basically we're saying, let's work with 46.87 cis 1.38. Okay, remember that 1.38 is in radians. So what we should do now is we should convert that into Cartesian form, and let's see what our answer is compared to 9 plus 46i. So let's press menu. Then we want to select number by pressing 2. We want to select complex number tools by pressing 9. And this time, to convert to Cartesian form, we're going to convert to rectangular form. So we're going to choose convert to rectangular by pressing 7. So that looks good. Press enter and we get a representation for z cubed, correct to 2 decimal places, of 8.89 plus 46.02i. And notice that that is a little bit different to 9 plus 46i. And the reason for that is that the method that we were asked to use in part C produces approximately the same z cubed, not exactly, but approximately. And the differences we're seeing here in the calculations is as a result of rounding in the calculations. So the reasonableness is fine. We can just conclude that the differences are due to numerical rounding. Question 13A is worth 1 mark. We're asked to consider a situation regarding customer waiting times, which are normally distributed. And the claim from the company is that the mean wait time for customers is 7.6 minutes. What's happened here is that a random sample of 12 customers has been taken and their wait times are obviously recorded in that table there. Part A asks us to determine the sample mean wait time from this sample. What you can see on the screen is I've already taken the liberty of entering the data into a list and spreadsheet application. And notice that I have called the variable for this data is X. Just to ensure that I've got all 12 points in, if you press Control 1, takes you to the bottom of the column, and Control 7 takes you to the top. Okay, so let's calculate this sample mean wait time. What we're going to do is we're going to press, we can do this either in a calculator application or in the list and spreadsheet application. While we're here, let's do it in the list and spreadsheet application. We're going to press Menu. We're going to select Statistics by pressing 4. We're going to select Stat Calculations by pressing 1 or Enter, and then 1 or Enter for one variable statistics. The number of lists is 1, so we can press Tab to highlight OK and then press Enter. Now our X1 list, if I arrow to the right with the navigation pad, I'm going to choose X. Frequency list is good, don't need to worry about categories. And the first result, column B, is good because column B is currently clear. So if I can press Tab all the way down to OK and press Enter, what we can see there quickly is if I move down to cell C2 and toggle between B2 and C2, the sample mean, X bar in this instance, is equal to 9.233, etc. So the sample mean wait time for this sample, correct to 2 decimal places, is 9.23 minutes. Question 13B is worth 3 marks. We're told that the standard deviation of this data in the sample can be calculated to be 2.384, correct to 3 decimal places. And we're asked to find an approximate 95% confidence interval for the mean to evaluate the reasonableness of the company's claim. So I've opened up a calculator application or a calculator page here, and we're going to perform a particular confidence interval calculation called a Z interval. So what we're going to do now is we're going to press menu. Then I'd like to select statistics by pressing 6. Then I'd like to select confidence intervals by pressing 6. And then it is 1 or enter for Z interval. We've got a choice here of using data or stats. If I arrow to the right with the navigation pad, arrow down, choose stats, press tab to highlight OK, and press enter. And what we can do is we can use the anchor stats that have been stored when we performed the one variable statistics calculation in part A to find the sample mean. So for our first field, we're going to choose the standard deviation, which is denoted by stat.sx. Press tab. Use our navigation pad to the right again, and we're going to use stat x bar for the mean. Press tab. Now we know that there's 12 points. We could also press stat.n. Press tab. Our confidence level 0.95 or 95%, so we don't need to alter that. Press tab to highlight OK, and then press enter. And what we find is our confidence interval, correct to 2 decimal places, the lower limit is 7.88 and the upper limit is 10.58. Notice there that our sample mean is denoted as 9.233, etc. ME stands for the margin of error, and basically that's the width of, or gives you a measure of the width of the confidence interval. Also notice there that our standard deviation 2.38416. All right, in the question we were told it was 2.384, correct to 3 decimal places. So let's examine the company's claim. So the company claimed that the population mean wait time was 7.6 minutes. Now 7.6 minutes is a value that is not contained within this confidence interval. So therefore we can conclude that the company's claim is not reasonable, as the population mean wait time as claimed lies outside this confidence interval. Question 14 is worth 4 marks. At a certain location, a biologist measures the width of a river to be 12 metres. Also, the biologist records the depth of the river at regular 2-metre interval widths. The biologist estimates that the cross-sectional area of the river at this location, she estimates it to be 15 square metres. What we're asked to do is we're asked to use Simpson's rule to estimate the cross-sectional area of the river at this location and to evaluate the reasonableness of the biologist's estimate. So the interval width W is equal to 2. And so applying Simpson's rule formula, we can say that our estimate using Simpson's rule is going to be given by 2/3. So let's first of all press Control divided by to access the fraction template. Enter 2 in the numerator, arrow down, and 3 in the denominator. And then come back level with the vinculum. Press the multiplication key. Open up our first bracket. Then we're going to enter these measurements according to the Simpson's formula. So 0.52 plus 4 times, open bracket, 2.15 plus 4.27 plus 1.28, and close that bracket, plus 2 times, open bracket, 3.70 plus 3.32, navigation pad to the right, plus 0.59. We've got a natural closing bracket there. We press enter. And so we obtain the answer 30.633, etc. for Simpson's rules estimate for the cross-sectional area of the river. So let's compare that to the biologist. Now, the biologist's estimate of the area of 15 square meters is less than half of the value obtained using Simpson's rule. Hence, we can conclude here that this estimation is not reasonable. Question 15A is worth 2 marks. We're told that travel times for students attending a certain university are normally distributed with a mean of 25.2 minutes and a standard deviation of 4.7 minutes. Travel times are collected from a random sample of 120 of these students and used to calculate a sample mean x1 bar in minutes. Part A asks us to find the probability that the sample mean is less than or equal to 25 minutes. So, a couple of points regarding the background here. The sample mean x bar is also normally distributed, and we can say that the mean is the same as the population mean, but note that the standard deviation is going to be equal to 4.7 on the square root of 120, where n is 120, that's the sample size. So basically, if we know that a random variable has a normal distribution and that we know mu and sigma, then we also know the distribution of the sample mean. So we're going to use the normal CDF command here, and we must ensure that we use the correct standard deviation. So let's first of all press menu. We're going to select probability by pressing 5. We're going to select distributions by pressing 5. And we're going to select normal CDF by pressing 2. And a normal CDF dialog box appears on the screen. Now that's a very large lower bound. Normally something like negative 10,000 will suffice. So let's have a lower bound of, say, negative 10,000. Press Tab. Now our upper bound is 25. Press Tab. The mean, which is the population mean, is 25.2. Press Tab. And now this is important. This is not 4.7. It's 4.7 divided by Control X squared to get the square root sign. Enter 120 and close the bracket. Press Tab to highlight OK and then press Enter. And what we see there is an answer of 0.320, etc. So what does this answer mean? What have we found? We've found that the probability of x1 bar less than or equal to 25 is equal to 0.32, corrected 2 decimal places. So the probability that the sample mean is less than or equal to 25 is 0.32. Question 15b is worth 1 mark, and we're asked to find the value of k, which is a time in minutes, given that the probability that the sample mean is greater than k is equal to 0.9. So I would advise you to draw a normal distribution curve diagram. Bell-shaped curve, vertical line in the center representing 25, and then a vertical line to the left of 25, denote that by K, and then shade in the area to the right. So in other words, you're shading in 90% of the area under the curve that's bounded by that vertical line representing K. That means that there's 10% to the left that is unshaded. So in other words, we can also say that we can find K for which the probability that x1 bar less than K is equal to 1 minus 0.9, or in other words, 0.1. And that's the way that the inverse normal command works on Nspire. So let's now find the inverse normal command and let's enter in what's required to answer this question. Let's press Menu, then probability. We want to select probability, so we'll press 5. We want to select distribution, so we press 5. And we want to select inverse normal, so we'll press 3. And the inverse normal dialog box appears. So for the area, you could type in 0.1. We will type in 1 minus 0.9. Press Tab. The mean is 25.2. Press Tab. And the standard deviation, remember that it is 4.7 divided by the square root. Square root symbol is accessed by pressing Control X squared. 120, which is the sample size. Close the bracket. Press Tab to highlight OK, and then press Enter. And we get a K value correct to 2 decimal places of 24.65. And in fact, that is 24.65 minutes. Question 15C is worth 4 marks. We're told that travel times are collected from a second random sample of the university students and used to calculate a second sample mean, x2 bar, which is also measured in minutes. We're told that the probability that x2 bar less than or equal to 25 is approximately equal to 0.4, and given that, we're asked to determine the number of students who took part in that second random sample. Okay, so our first approach here is to take that given probability interval and turn it into a corresponding Z value. So what we want to do now is we want to work with the standard normal distribution. And to preserve continuity in the calculations, what I'd like to do is I'd like to assign Z2. So to access the assign command, control symbols template, I'd like to assign Z2 to be the following. Now I want to find the inverse normal command. So we're going to press menu. Then I want to select probability by pressing 5. I want to select distributions by pressing 5. And I want to select inverse normal by pressing 3. Now the area is 0.4. And I would like the mean to be 0 and the standard deviation to be 1. So in other words, we're looking at the standard normal distribution. Tab all the way through to highlight OK and press enter. And what you see there is that Z2 has a value and it's negative 0.253, etc. Now what we're going to do is we're going to set that equal to 25 minus 25.2 on 4.7 divided by the square root of n and solve for n. And that will give us the sample size. So it's a linear equation, so we can use the numerical solve with confidence. So we're going to press menu. To select algebra, I'm going to press 3 and then 1 or enter for numerical solve. And the equation we're going to solve is we're going to solve, so if you press var, highlight Z2 and press enter, you could have typed it in. Z2 is going to equal control divided by to get a fraction template. So it's 25 minus 25.2. Navigation pad down to the denominator. And we need another fraction here. So control divided by. Enter 4.7. Navigation pad down. Control X squared. And here we'll type in n. Then navigation pad to the right once, twice, 3 times. We want to solve for n. So the way we denote that is comma n. Press enter. And we get 35.446, which means that the required sample size for the number of students in the second sample is 35. Question 16 is worth 6 marks And having a look at the wording, it says that a curve modelled by the relation xy squared minus y plus inverse cos 2x equals 1, where x lies between negative 0.35 and 0.27, and y lies between 0 and 1, intersects the y-axis at point A. In this question, we are asked to determine the equation of the tangent to the curve at point A. So first of all, our solution plan, our first step in the solution plan will be to find the y-coordinate of A. The equation of the tangent to the curve at A will have an equation form y equals mx plus c, where c is where the curve intersects the y-axis. So our first step is to find the y-coordinate of A. And the way we can do that is a fancy way. We're going to assign y to be the solution of an equation. So let's enter that now into Nspire. So first of all, we're going to denote the y-coordinate to be y. So y. Then the assign command is found by pressing Control symbols template. We want to find a command from the menu called numerical solve. So we press menu, we select 3 for algebra, and then 1 or enter for numerical solve. And what we're going to do now is we're going to enter the relation. So we're going to type in x times y squared minus y plus, now to find the inverse cos, we'll press trig, and then we'll scroll across and down with the navigation pad to highlight inverse cos. Press enter, and we'll enter 2 times x. Navigation pad to the right, set that equal to 1. And what we want to do is we want to solve for y, so comma y, and then navigation pad to the right, and come out of that syntax, and we want to say, okay, on the y-axis, x is equal to 0. So we want to solve this given x is equal to 0. So if we press Control equals, navigation pad to the left, that highlights the with or the given symbol. Press enter, and then we will add the condition x equals 0. Press enter, and when x is equal to 0, y is equal to 0.5707, etc. So we have determined the y-coordinate of A. The next part of the solution plan does not involve the calculator, it involves by hand mathematics. And what we need to do here is, given that relation, we need to use implicit differentiation to find dy dx, and then rearrange our expression for dy dx to make dy dx the subject. And when you do that, you obtain that dy dx is equal to 2 on the square root of 1 minus 4x squared. And that is all minus y squared on a numerator, and a denominator of 2xy minus 1. What we need to do then is we need to substitute x equals 0 into our expression for dy dx, and also our y value, which is 0.5707, and that should give us a measure of dy dx at the point A. So it's quite a complicated expression to enter on Nspire. First of all, we press Control divided by to enter a first fraction template, and then Control divided by to enter a second fraction template. In this first numerator, we will enter 2. Navigation pad down. Here we will enter the square root of 1 minus 4x squared. So Control x squared, 1 minus 4 times x squared. Navigation pad to the right once, and now twice to bring it outside that fraction, and the cursor is level with that vinculum. Subtract y squared. Now notice that y is bold and non-italicized because that y we've found that to be 0.5707, etc. on that previous entry line. Now come down with the navigation pad into the denominator there, and we will type in 2 times x times y, notice it's bold and non-italicized, minus 1. Now we press the navigation pad to the right once to come out of that expression, and what we need to do now is to add that condition that we want to evaluate this when x is equal to 0. So again, Control equals, navigation pad to the left to highlight the width or the given symbol, press enter, and then add in the condition x equals 0 and press enter. And what we find there is that dy dx at point A is negative 1.67. Now the equation of the tangent is in the form y equals mx plus c, and on the screen there we have a value for m and we have a value for c. So we have indeed answered the question. All we need to do now is interpret the output. And what we can see is that the tangent to the curve at A, correct to 2 decimal places, is given by y equals negative 1.67 plus 0.57. And that is the answer to question 16. Question 17 is worth 6 marks. We're told that an object is projected upwards from ground level with an initial velocity of 15 meters per second at an angle of 54 degrees to the horizontal. The object just passes over a drone that is hovering in the air. An observer is positioned directly below the drone and at a horizontal distance of 20 meters from where the object is projected. The observer makes 2 comments about the motion of the object. First of all, the observer says that it took the object around 2 to 2.5 seconds after projection to reach the drone. And the second comment is that the object was still moving in an upwards direction as it passed the drone. Assuming that air resistance is negligible, we are asked to use a vector calculus approach to evaluate the reasonableness of the observer's comments. In other words, we're going to analyse the 2 claims made by the observer. Now, let's set up our model. First of all, we're going to let vectors I and j be the horizontal and vertical unit vectors respectively. And we're going to let t represent the time in seconds after the object is projected. So we can therefore say that vector a of t, which represents the acceleration of the object, is equal to negative 9.8 times unit vector j. Anti-differentiating both sides, we therefore obtain that vector v of t is equal to negative 9.8 times t times unit vector j plus a constant vector c. Now, when t is equal to 0, v is equal to c, and so therefore we can say that c, vector c, is equal to 15 cos 54 degrees I plus 15 sine 54 degrees j. And we can therefore say that v of t is equal to 15 cos 54 degrees I plus 15 sine 54 degrees minus 9.8 t j. That is our vector for the velocity of the object. Now, let's first of all look at the observer's first claim. We know that in the horizontal direction, that v of t is equal to 15 cos 54 degrees. So therefore, if we were looking at the horizontal component and looking at the distance travelled in the horizontal direction, x of t is equal to 15 times cos 54 degrees multiplied by t. And a reminder that the observer is 20 metres away from the point of projection. So what we can do to test the observer's first claim is to substitute t equals 2 and t equals 2.5 into x of t equals 15 cos 54 degrees times t and determine the reasonableness of the observer's claim. So let's go to Nspire, and if you have a look here, I'm in radian mode. So let's type in first of all 15 multiplied by, press trig, nav pad to the right to highlight cos, and press enter, then enter 54. And what we need here is the degrees symbol. So if I press the pi button, down with the navigation pad to highlight that degrees symbol and press enter. There's our 15 times cos 54 degrees. Now, navigation pad to the right. What we can do is we can perform this substitution of t equals 2 and t equals 2.5 in one step. We'll press the multiplication key. Then what we'll do is we'll enter 2 and 2.5 as a list. So if we press Control and then the normal closing bracket, that brings up the curly brackets that represent lists. And we will enter 2, then a comma, and then 2.5. And it's best for us to obtain decimal answers here. So what we will do to obtain our values for x at t equals 2 and t equals 2.5 is we'll press Control Enter. Notice above the enter you've got an approximately equal symbol. And we obtain the values 17.63 and 22.04. So what have we found here? We can say, therefore, that at t equals 2, x is equal to 17.63 metres, and at t equals 2.5, x is equal to 22.04 metres. Both those distances correct to 2 decimal places. Now, the observer is 20 metres away from the point of projection. So the observer's time estimate for the object to reach the drone is indeed reasonable. So the observer's first claim is reasonable. The observer's second claim, we need to look at it again and say that the observer was believing that the object was still moving upwards as it passed the drone. So what we will do now is we'll test that claim by considering the vertical component of velocity at t equals 2. In other words, we're going to substitute t equals 2 into 15 sine 54 degrees minus 9.8 times t. So let's enter that in now. So we'll enter the 15 multiplied by, press trig, sine's already highlighted, so press enter. 54, press the pi button, down navigation pad to highlight the degree symbol, press enter, navigation pad 1 to the right, minus 9.8 multiplied by t. We want to evaluate that when t equals 2. So we will press Control equals, navigation pad to the left to highlight the with or the given symbol, press enter, and then we will substitute t equals 2. Press enter, and we get a velocity, the vertical component of velocity, to be negative 7.46, etc., meters per second. Now, the positive direction here is upwards. That velocity is negative, it's less than 0. So in other words, the vertical component of velocity of the object is acting in a downwards direction. So the object at t equals 2 would have been moving in a downward direction. And so the observer's comment on the object's direction of motion is not reasonable. And that concludes our analysis of the observer's claims stated in question 17. Question 18 is worth 5 marks, and we are asked to consider the complex solutions to the following equation, where the arg of z lies between 0 and pi, not including 0 and not including pi. And it's quite a complicated looking equation. It's z plus 1 multiplied by a bracket that includes z to the 14 minus z to the 13 all the way down to plus z squared minus z equals 1 minus z. We're told that W1 is the solution with the maximum possible real part, and we're told that W2 is the solution with the maximum possible imaginary part. We're asked to show that W1 to the power of 4 divided by W2 is an integer. So what we need to do is we need to calculate those two quantities, form the quotient, and hopefully obtain an integer answer. Now what we need to do is we need to look at this rather fearsome looking equation. And if we, on the left-hand side, we multiply out the brackets and then add z minus 1 to both sides so that the equation is set to 0, what you can quickly see is that this equation is a disguised roots of unity equation. And so this original equation simplifies to z to the power of 15 equals 1. And so therefore we can say that z is equal to cis 2k pi on 15, where k is an integer, and of course the arg of z lies between 0 and pi, not including. So let's look at W1. The root with the maximum possible real part will occur for a k value equal to 1, which corresponds to a real part of cos 2 pi on 15, which is a value It's about 0.91, and it's a value that's just below 1. So we can therefore conclude that W1 is equal to cis 2 pi on 15. The root with the solution with the maximum possible imaginary part will occur for k equals 4. And so therefore W2 will equal cis 8 pi on 15. And that's because the imaginary part is sine 8 pi on 15. And that's a value that's around about 0.99 and again just below 1. So we have W2 and W1. It's a matter of forming the expression W1 to the power of 4 divided by W2. W1 to the power of 4 using de Moivre's theorem is cis 4 times 2 pi on 15, which is cis 8 pi on 15. W2 is also cis 8 pi on 15. And so cis 8 pi on 15 divided by cis 8 pi on 15 is equal to 1, which is an integer. What we can do with Nspire is we can confirm our by-hand mathematics. So let's show you now how to confirm this with Nspire. In other words, we're going to check our mathematics and make sure that we have correctly answered the question. We can start off by assigning W1, so W1, control symbols template. We can assign it to be cis 2 pi on 15, but we can't enter cis 2 pi on 15. What we're going to enter is e to the power of 2 pi I on 15. So we press our e to the x button, don't press letter E, then control divided by for the fraction template, then it's 2 multiplied by, press the pi button, pi is highlighted, press enter, press the multiplication key, go back to the pi button, navigation pad to the right to highlight complex number I, press enter, navigation pad down into that denominator box, type in 15 and then press enter. And that actually confirms quite nicely that that's cis 2 pi on 15. Now let's enter W2. W2, control symbols template. Now W2 is going to be, we press E to the X button, then control divided by for the fraction template. And that's going to be 8 multiplied by pi multiplied by complex number I, down, and then enter 15 there in the denominator, and then press enter. And that's what the Nspire gives us for W2. And now what we can do is we can form this expression W1 to the power of 4 divided by W2. So therefore, W2, well, let's first of all get the fraction template, control divided by. And now if we press var, which is short for variable, notice that we can call up W1 and W2 because we've assigned them. So let's first of all call up W1. It's highlighted, so we'll press enter and then press the exponentiate key and raise W1 to the power of 4. Navigation pad down into the denominator box. Press the var key again, down with our navigation pad to highlight W2. Press enter and press enter. And we get a real mess. However, if we press control enter, what we get is we get an answer that we need to interpret It's 1 plus a number which is so vanishingly small that we can say that the calculator has confirmed to us that W1 to the power of 4 divided by W2 does indeed give us 1, which is an integer. So this is an example of a question which is most definitely best done without a calculator, but you can use your Nspire to confirm the result. Question 19, the final question in the paper, is worth 7 marks. The height of Year 9 students at a school is assumed to be normally distributed with a population mean height of mu centimetres. A teacher at the school measured the height of all the students in her Year 9 class. This data was used to calculate an approximate 95% confidence interval for mu, and she obtained a confidence interval of 163.7 to 166.9 centimetres. The teacher then repeated the procedure using data from another Year 9 class. This class had the same number of students, and the data produced an approximate 95% confidence interval for mu of 167.8 to 172.4 centimetres. Using the same data, the teacher recalculated the approximate confidence intervals for mu for each class using a confidence level of X%. And what the teacher observed was that the upper bound of the confidence interval from her Year 9 class now equaled the lower bound of the confidence interval from the other Year 9 class. What we're asked to do is we're asked to use that information to determine the value of X and give our answer correct to 1 decimal place. Let's have a look at a solution. First thing to note is that the Z-score for approximate 95% confidence intervals, correct to 2 decimal places, is 1.96. Let's first of all have a look at the teacher's Year 9 class, and our first step is to calculate the teacher's class sample mean. And what we're going to do is we're going to use the calculator and give this sample mean an assigned value. So the teacher's class sample mean, let's call it X1 bar, it's equal to 163.7 plus 166.9 divided by 2. So the lower bound plus the upper bound divided by 2 of that given confidence interval. So what we're going to do is we're going to type in X1 bar, and we're going to assign that by pressing Control symbols template. We're going to assign that to be Control divided by, to insert the fraction template, 163.7 plus 166.9, down with the navigation pad into the denominator box, divided by 2, and press Enter. So we've stored or assigned X1 bar to be 165.3 centimetres. Now let's let S1 be the sample standard deviation for sample size N for the teacher's class. And what we're going to do now is we're going to form an equation, and we're going to determine the value of S1 on root N. So I'm now going to assign a new quantity. I'm going to assign SE1, which is going to be S1 on root N. I'm going to assign that to be the solution to an equation. So Control symbols template for the assign command. Now to find the numerical solve command, we press Menu then I'm going to select algebra by pressing 3 and then 1 or enter for numerical solve. And the equation I want to solve here is 165.3, which is x1 bar, plus 1.96 times s1 on the square root of n equals 166.9, and I want to solve it for s1 on root n. So let's enter that. If I press var, which is short for variable, I can call up x1 bar rather than typing it out again, plus 1.96 multiplied by, now I'm going to assign, as I've said, SE1 to be S1 on root n. So we're going to multiply it by SE1, set that equal to 166.9. And we're going to solve for SE1, so comma, SE1, and press enter. And we get an S1 on root n value of 0.816, etc. What we're going to do now is we're going to repeat this approach for the other class. So the other class, the sample mean, let's call it x2 bar, it's equal to 167.8 plus 172.4 divided by 2. Now what we can do is we can go up to our first entry and edit it. We press enter, bring it down to a new entry line, and then using the navigation pad we can come across here and we can change, press the backspace button, we can change that 1 to a 2, and then what we can do is we can edit the numerator. So the numerator we can write as 167.8 plus 172.4 divided by 2. Press enter, and we get x2 bar to be 170.1. And what we're going to do now is we're going to edit this equation, and we're going to form a second equation. We're going to let S2 be the sample standard deviation for the sample size n. We're going to assign S2, we're going to assign SE2, we're going to assign SE2 to be S2 on root n. So all we need to do now is to edit this equation. So SE2 is x2 bar plus 196 times SE2. We're going to set that equal to 172.4. And we are going to solve for SE2. Press enter. And so we therefore get an S2 on root n value of 1.173. Now, we are told that the upper bound of the teacher's class confidence interval is now equal to the lower bound of the other class's confidence interval. So we now need to form an equation. We need to perform some by hand algebra. And let's see what that looks like. We're going to let Z subscript X be the Z score for the X percentage confidence interval, the approximate X percentage confidence interval. And as I've said, the upper bound of the teacher's class confidence interval is now considered to be equal to the lower bound of the other class's confidence interval. And we can express that as an equation. The left-hand side is the upper bound of the teacher's class. So it's x1 bar plus zx times s1 on the square root of n. We equate that to the lower bound of the other class's confidence interval. So we equate it to x2 bar minus zx times s2 on the square root of n. Now, on Inspire, SE1 is S1 on root n, and on Inspire here, SE2 is S2 on root n. So our goal is to rearrange that equation to make ZX the subject. And so what we've done there is we have added ZX S2 on root n to both sides and subtracted x1 bar from both sides to form line 2 there. And then it's a matter of dividing both sides by s1 on root n plus s2 on root n to give us an expression for zx, which is our z score for the approximate x percent confidence interval. Now, if we have a look at this expression, on Inspire, we have x1 bar assigned, x2 bar assigned, SE1 assigned, SE2 assigned. So if we go back to our calculator application, what we can do now is we can say, well, okay, let's assign ZX, so control symbols template. Let's assign that to be control divided by the fraction template. We're going to be using the var key here to call up our assigned variables. It's going to be x2 bar minus, pressing var again, x1 bar, come down to the denominator, and it's going to be SE1 plus, it's the variable key again, SE2, and press enter. And we get a Z score for an approximate X percentage confidence interval of 2.412, etc. Perfect. Now what we can do is use the normal CDF command to calculate the corresponding probability, which will give us X, and we can express that as a percentage. So our final step in this rather detailed calculation is to press menu, then select probability by pressing 5, select distributions by pressing 5, and then select normal CDF by pressing 2. Now we get our normal CDF dialog box here, our lower bound is going to be negative, and then if we press the variable key, nothing happens. That's okay. We can type in ZX, press tab. For the upper bound, we can press ZX, press tab. We're dealing with a standard normal distribution here. So our mean is 0 and our standard deviation is 1. Then tab to highlight OK and press enter. And it gives us 0.984, etc., etc. So therefore, X is equal to 98.4, correct to 1 decimal place. And that we can now confirm that the teacher for each class used a confidence level of 98.4%.